Hello students, we have discussed already in the previous video about the so many characteristic of group 15, in which we have given the more focus on the oxidation state. In oxidation state we have discussed nitrogen show the number of oxidation state in a compound. In case of oxygen, we show +3, -3 about the nitrogen, -3, -2, -1, 0, +1, +2, +3, +4 in N2O4 and +5 in N2O5. So students, in case of nitrogen, all oxidation state tend to undergoes disproportionation in acidic medium. Disproportionation in the acidic medium. For example, HNO2, in which nitrogen in the +3 oxidation state, when it undergoes to slightly heating medium, it is decomposed or dissociate to form nitric acid and nitric oxide and H2. So here the nitrogen on the +3 oxidation state, in HNO3 the oxidation state of nitrogen becomes 5, and in the nitric oxide the oxidation state becomes 2. This is nitric acid, and this is nitric oxide. So this is the example of nitrogen. If the oxidation state present in middle of the oxidation state, it undergoes to disproportionation reaction. In case of phosphorus also, you can see in case of phosphorus it also undergoes to disproportionation reaction. Phosphorus acid, in which phosphorus is +3 oxidation state, and when it disproportionate reaction show, it becomes H3PO4 plus PH3. It is known as phosphine gas. So here the phosphorus present in +5 oxidation state, but in case of phosphorus hydride or phosphine, it present in a -3 oxidation state. Let's see the chemical property, means reactivity of nitrogen with hydrogen at first. Reactivity towards hydrogen. All the members of group 15, when react with hydrogen, it forms hydride. Nitrogen hydride, phosphorus hydride, arsenic hydride, antimony hydride and bismuth hydride. All the members have tendency to form hydride with hydrogen. So we see the nature of hydride. It is covalent in nature. Covalent hydride, we call it covalent hydride, and all the central atom has sp3 hybridized, like if we symbolize the group of atom by M and 3 hydrogen and 1 lone pair present there. So hydrides of this group, in which hybridization of central atom is sp3. So student, at first we know the nature of hydrides. It is the covalent hydride and it is pyramidal in shape, and central atom is sp3 hybridized. This is the common things which we remember all the time. And let's first discuss the preparation of hydride. How can we prepare the hydrides? Suppose for preparing hydrides of this group, we take the salts of particular metals. Suppose we have magnesium nitride. This is the salts of nitride. When it undergoes to hydrolysis, it will form magnesium hydroxide and our desired product NH3 will form. So balance is also same things. A phosphides compound taken, suppose we have phosphides compound, so when it undergoes to hydrolysis, it will form calcium hydroxide and we have hydrides of phosphorus. So balance it. In this way we can prepare the hydrides of particular group by hydrolyzing hydrolysis of particular salts. So this gives the hydrides of that particular group. Now we discuss the structure of hydrides. We have already discussed. So let's discuss the characteristic of hydrides. At first we discuss the bond angle. Bond angle, as we know, down the group electronegativity decrease. Suppose we have NH3, PH3, ASH3, SpH3 and bismuth S3. We have the hydrides of particular group. So as we know, down the group electronegativity decreases, so that bond angle also decreases. So when we move top to bottom, bond angle decreases. Because electronegativity of the atom decreases. As size of central atom increases due to the gradual decrease in the force of repulsion among the shared and electron pair. Suppose we have a structure like this. As we move from top to bottom, the size of central atom increases, so that the decrease in the force of repulsion between lone pair and shared pair of electron. That is the reason for decreasing the bond angle when we move top to bottom in a specific hydrides. So students, learn it when we are going to arrange in the increasing or decreasing order of bond angle. So we discuss, as we move top to bottom in a group, the size of atom increases, so the repulsion between lone pair and shared pair decreases, so that their bond angle also decreases. Next we discuss the basic strength. Basic strength of hydride. Basic strength also decreases When we move top to bottom, simply write here basic in strength also decreases. So most basic in nature is NH3, then PH3, then arsenic hydride, then antimony hydride, and least basic in nature is bismuth hydride. Electron releasing tendency is maximum in nitrogen due to high electron density. Maximum in nitrogen due to high electron density and small in size. So simply we can write why this particular hydrides of nitrogen is more basic in nature. So we can write small size and high electron density. Next, the characteristic is thermal stability. Thermal stability. Thermal stability. Students, thermal stability inversely proportional to the thermal stability is inversely proportional to the MH bond. This is MH bond length. The bond length increases from ammonia to bismuth hydride because increase in the size of central atom. The bond dissociation enthalpy decreases and therefore stability decreases from ammonia to bismuth. Simply or very easy to explain what is the criteria of thermal stability when we move top to bottom. Next, reducing nature. Reducing nature of hydride. It increases from NH3 to PiH3, means bismuth hydride. The reducing nature is related to thermal stability. As we know, the reducing nature is related to thermal stability. Lesser the thermal stability, more will be the reducing nature. More will be the reducing nature. So in that condition, bismuth hydride is maximum reducing character since it is least stable in nature. So we can write here also bismuth hydride is the maximum reducing nature. Due to its least stability in nature. Due to it is least stable in nature. This type of a small points becomes reasoning questions sometimes. Now the boiling point. Next property is the boiling point. Next is the boiling point. The boiling point increases down the group because increase in the magnitude of the van der Waals force of attraction, which depends upon the molecular size. The general characteristic, we know that as the size of atom increases, their molar mass increases because van der Waals force of attraction increases. So we know that when we move top to bottom, the size of atom increases. But in case of ammonia, we know that ammonia have high boiling point due to H bonding. So here is the trend slightly changing. So PH3, then arsenic hydride, then NH3, then antimony hydride, and then bismuth hydride. So the regular trend is slightly changed because the boiling point becomes high due to in ammonia due to H bonding. We know the nature of ammonia, it forms H bonding, so the boiling point arranged in this form. But general trend is, as we know, boiling point increases down the group because increase in the magnitude of van der Waals force of attraction, which depend upon the van der Waals force of attraction. So students, let's discuss about the melting point, boiling point and melting point. Melting points of hydride, phosphorus hydride, then arsenic hydride, then antimony hydrides, and maximum melting point of nitrogen hydrides because of H bonding. NH3 has high melting point in the down the group, molecular size increases, van der Waals force of attraction increases, melting point increases. But nitrogen hydride is highest melting point among the group because of presence of hydrogen bond. So we can write also due to H bond. This trend is very important to learn or arrange. Always this type of question were asked in the examination. Now reactivity towards the halogen. Let's we discuss the reactivity towards the halogen. Halogen. These elements react to form two types of halide compound, EX3 and EX5, because this group show two types of oxidation state, in fact variable oxidation state, +3 and +5, +3 and +5. So two types of halides compound formed by this group. Here is the exceptional case about the nitrogen. Nitrogen does not form NX5. It can only form NX3 because it has no d orbital. Or unavailability of d orbital. Nitrogen cannot form pentahalide, but other members can form pentahalide easily. With the exception of NX3, other members can form both type of halides, trihalides and pentahalides. Nitrogen can form exceptional trihalides like NCl3, NBr3 and Ni3. All other trihalides are stable. With the exception of this, all other trihalides are stable due to weak NCl or NBr and Ni bond. So write down the statement also with the right here. Nitrogen does not form pentahalides. Nitrogen does not form pentahalides due to unavailability of d orbital. With the exceptions of nitrogen trichloride, nitrogen bromide, nitrogen tribromide and nitrogen triiodide, all other trihalides are stable due to weak NCl and weak NBr bond and Ni bonds. On account of large difference in the atomic size, these are not so stable because there is a large difference in their size. Nitrogen is very small in size, whereas chlorine is larger in size, bromine is larger in size, iodide much more larger in size. So their bond is not so stable. Exception of this, apart from this and this, all other halides are stable. So students, Lewis acid character in the halides is central atom is also sp3 hybridized, structure of EX3, trihalides, structure of trihalides, and the shape is pyramidal shape. So students, Lewis acid strength increases down the group due to Lewis acid strength. Lewis acid strength increases down the group. PCl3, AlCl3 and more. Lewis acidic character is AlCl3. Antimony, suppose antimony trifluoride have tendency to take two fluoride ion to form antimony pentahalides. Antimony pentahalides. So this is Lewis acid and this is Lewis base. Lewis base. With the exception of nitrogen, can act as a Lewis base. So in this group, trihalides, with the exception of nitrogen, it can act as a Lewis nitrogen, all members can act as a Lewis acid by accepting an electron pair to the vacant d orbital due to vacant d orbital. Only nitrogen cannot behave as a Lewis acid because it has no vacant d orbital. It behaves as a Lewis base. In trihalide, we are studying about the trihalide. All the members are leaves acid in nature because it can accept lone pair electrons. So structure of this is the trihalide MX3, and here is the lone pair present, and the hybridization is sp3. Next we discuss about the px or pentahalide EX5. So student, the structure of EX5, and first we discuss about the structure of EX5 trihalide, one pair. So the structure will be trigonal, gonal, bipyramidal, and the hybridization of central element is sp3d. 1, 2, 3, 4 and 5 bonds is there, so the hybridization will be sp3d. These are not very stable. These are not very stable on account of difference in the bond length. This bond length is 120 and this bond length is 90. So their bond length difference makes it unstable. It is easily decomposed to PCl3. So PCl5, for example, we take PCl5, it quickly decomposes to PCl3 and chlorine due to difference in bond length angle. So students, the axial and equatorial bond length is the difference in the axial and equatorial. This is called the equatorial, this is called the axial bond length. So the difference in the bond length of axial and equatorial bond, PCl5 easily dissociate to form PCl3 and Cl3. So due to this property, it acts as a chlorinating agent. PCl5 is act as a chlorinating agent because this question is sometimes this type of questions may ask in examination why PCl5 is not stable, easily readily decomposed to form phosphorus trichloride and chlorine. So we give their answer due to equatorial and axial bond length. This is equatorial bond length, this is the axial bond length. So difference in the bond length of equatorial and axial bond, so it readily decomposed to form phosphorus trichloride and the chlorine.